Hello and welcome to this technical overview session in which we will cover Opni. Opni is a multi-cluster, multi-tenant observability platform that comes with AIOps capabilities. We'll kick off by talking about observability, followed by a talk and demo of Opni's core logging, monitoring, and AIOps features. My name is Sanjay Nadhavajhala, and joining me are Dan Bason, Amartya Chakraborty, and Yingbei Tong. Dan leads Opni logging, Yingbei leads Opni AIOps, and Amartya is in charge of log anomaly detection. The classic definition of observability comes from system control theory, where observability is a measure of how well the internal states of a system can be inferred from knowledge of its external outputs, a kind of digital exhaust. It's the actionable insights you collect from your entire system, not just one component, that tells you the health of your environment. Current generation observability tools allow you to see the iceberg above the water. We believe that AI added to observability allows you to see the iceberg both above and beneath the surface, and that is what Opni aims to do. Majority of people collecting and leveraging observability data want to understand what's happening inside their system at any time. In addition, they want to immediately identify the problem when something breaks and just as quickly identify the solution to a problem. There are three pillars that are needed for observability. These pillars are logs, metrics, and traces. More data is always better, but without these, it will be difficult to get the benefits of observability. The good news is that so much data exists, especially in Kubernetes clusters. The challenge is aggregating and gaining insight from all of it. It's even more challenging in the open source world where logs, metrics, and traces all have several competing projects, with each of them only addressing one pillar. Not only must one collect this data, but they must also be able to send these forms of observability data to a system that can store and analyze it. Opni was built with all these points in mind. Collecting and leveraging observability data is typically a very expensive endeavor. One typically has to turn to a SaaS or be brave enough to set up one of the many open source alternatives, which we've seen to be very difficult to set up and manage. Opni aims to make the creation and management of observability tools and data easy. Similar to how Rancher made the creation and management of Kubernetes clusters easy, Opni does the same for observability. We make it easy to create and manage the backend for logs, metrics, and traces, as well as AIOps, including deep learning models that don't need any data, user configuration, or even a GPU to get started. Opni is completely open source, just like the other products in the SUSE Rancher landscape, and keeps Kubernetes first. It is a multi-cluster and multi-tenant solution that works very nicely with Rancher. On to Dan, who will be explaining Opni's infrastructure.
Thanks, Sanjay. So the first pillar of Opni observability is Opni monitoring. Now, you can't talk about monitoring in a Kubernetes cluster without mentioning Prometheus. It's the de facto standard and it's basically ubiquitous. If you're running a Kubernetes cluster and you want to monitor metrics, you're probably going to be running Prometheus. However, Prometheus does have some drawbacks. It is single cluster only, and to be able to access the metrics, you need to be able to go into that cluster and access the Prometheus data store that is running within it. That's not really what we want out of a true multi-cluster, multi-tenant monitoring solution. We need something that can aggregate all of the metrics into a central store. Now, there are already some solutions out there, things like Thanos, but there are some drawbacks to Thanos. It doesn't provide true fine-grained RBAC or multi-tenancy to be able to control who can see what metrics. That's why we've chosen to use Cortex. Cortex is a backend store that was originally created by Grafana and has been donated to the CNCF. It's one of the most active projects on the CNCF, and it is basically what it says on the tin, a backend store for Prometheus metrics with the ability to tag the metrics with multi-tenant information. In front of that, we have an API that sits in front of Cortex, and that's what provides all that extra stuff you need to get true multi-cluster and multi-tenant solutions. So it's got your authorization, your authentication, and an agent responsible for sitting in the downstream clusters and sending the cluster metrics to that centralized Cortex gateway. This is similar to an APM type solution where you deploy an agent, it does all of the monitoring, and then collects all of that and sends it back to a central solution where you can quickly view whether something's going wrong or if it looks out of place. The next piece of the Opni observability platform is Opni logging. Opni is based on OpenSearch. OpenSearch is a fork of Elasticsearch after Elasticsearch changed their license, so it was no longer able to bundle up Elasticsearch as an truly open source project. It was forked into OpenSearch, which is all under the Apache 2 license. To allow the user to easily ship their logs from downstream clusters, we set up a data prepper as our agent in the downstream, and this authenticates to the OpenSearch in the central cluster and sends its logs. What this means is that in the future, we will be able to support a tracing part of Opni logging. The other thing worth pointing out is that there is an official operator for OpenSearch. This is produced by a number of people from different companies in a true open source fashion, including SUSE. I am a maintainer in that project. Now, one of the things to note is that most logging systems, OpenSearch included, are very generic. They're built to, support a large variety of use cases. So what we wanted to do for Opni logging is drill down on that a little bit more and introduce Kubernetes clusters as first-class objects into that logging system. So what this means is that when a user is creating their role-based access or trying to manage the Kubernetes clusters within OpenSearch, they are first-class objects, and it makes the whole process of managing that very simple. So here we have a architecture diagram of the central Opni cluster. It uses the operator pattern, so we provide CRDs, and then it contains a number of controllers to manage the Kubernetes resources based on those CRDs. You can see here that it deploys a number of components. So we have the OpenSearch central cluster, we have the Cortex central cluster, that's for storing the metrics, and then we have the Opni gateway. And the Opni gateway is the control center for Opni. Provides a UI for managing downstream clusters as well as the RBAC for those clusters and setting up the initial token authentication for bootstrapping. Also provides an API that allows us to authorize and authenticate metrics remote writes from the Opni agents, and it integrates with OpenID if the user wishes, so we can put some authentication over the top of it. Here we have our central cluster that we're going to install Opni into. It's a EKS cluster that's been freshly set up, and the only thing that's been done to it is we've installed Cert Manager, which is a prerequisite for installing Opni. So the first thing we're going to do is go into the Rancher apps, and we're going to add a new Helm repository. So this repository that we're adding will contain the Opni charts. So we're going to go ahead and create it, give it a unique name, and we're going to select the Git repository, as it is a Git repository that contains our charts. Then we can copy and paste the URL from the Rancher chart setup under Opni logging. So we're just going to copy that and put it into the repo URL, and then the branch we're going to use is charts repo. So we install that here, click create, and we now have the Opni charts repo installed. So if we go to charts and then unselect all the others, we'll see that there are 3 charts in here. So the first thing we're going to install is the Opni Prometheus CRDs. So Opni requires the Prometheus CRDs to be able to set up the monitoring backend. So we'll go ahead and install that first. So we'll continue on and just hit next and install. And then we'll start installing this. Now that that's been successfully installed, we can go back to our charts and we can install Opni. So we're going to select that. We're going to select the latest version, which is 0.4.2. We're going to go install, and we're going to install it into Opni Cluster System namespace. This was a namespace that was automatically created by installing the Prometheus chart. So we'll hit next, and now we have some options that we can go through. So the first thing we need to do is choose a host name for the gateway. This is completely arbitrary, and this needs to be whatever your gateway will be exposed on so that downstream clusters can talk to it. This is the address of the API that the Opni agent will use to send metrics and to bootstrap clusters with. So we'll go ahead and put a URL in there. So this is the URL that we're going to use for the purposes of this demo. The next thing we need to go down and select is the authentication settings. So we're just going to use the NoAuth provider for the demo. And then we're going to enable monitoring. So the next URL we need to choose is the URL that Grafana will be exposed on. So again, this is arbitrary. It's whatever you want to choose to expose it on. So we're just going to put in a URL there. And then we have a number of potential storage backends for Grafana. So for the demo, we're just going to choose the file system backend. Then we'll move on to login. And again, we need to select an OpenSearch external URL. This is arbitrary, and this is the URL that the Opni shipper will index logs to. So rather than just a host name, this needs to be a full URL. So we'll go ahead and put that in there. Then we can choose to enable or disable persistent storage. We're going to enable it, and we're going to choose the storage class that we want to use to create the persistent volumes. And then we're going to choose whether or not to expose the OpenSearch data nodes. When you're indexing to OpenSearch, if you don't have an ingest pipeline, it's recommended that you index to the data nodes, which is why we have this option. And again, we can choose whichever one of these we want to use to expose it. We're going to be creating an ingress for the OpenSearch data nodes, so we're going to leave it as a cluster IP service. And finally, we're going to choose to enable the AI services, which will give us the Opni AI. So we'll go ahead and hit install and then wait for the install to complete. Now that the install has finished, we can see here it's completed successfully. We can go to the workloads for our namespace, and we can see that there are a number of pods created. So we have all the Cortex backend, we have an etcd storage, we have Opni gateway, and we have a number of inference services, as well as everything else required for Opni. And if we go under stateful sets, we can see that we have Opni master and Opni nodes, which are OpenSearch data nodes. If we go to the dashboard, we can see that we have an OpenSearch dashboards deployment that we can expose as well. We can log into this. If we go to discover, we can see that although we've got no logs in our system at the moment, the Opni controllers have set up a index pattern for us, and looking at the index setup, we can see that they have created a number of rollover policies and indices for us. Likewise, we can go to the Opni gateway. Now this has been exposed as a port forward using kubectl because Opni monitoring the UI is not supposed to be open to the world. It's for internal cluster use only. But you can choose to expose this using an ingress on an internal network if you choose. We can see here that we have a number of management options. And so that ends the demo of the central cluster setup. So now that we've got the central cluster set up, we can take a look at the agent architecture. So this is what gets installed into a downstream cluster. It's quite simple. There's not a lot going on. We use FluentD to gather the logs from the Kubernetes cluster and then send them to the Opni shipper, which is the data prepper instance, which is then responsible for sending them onto OpenSearch after a little bit of pre-processing. We also run Prometheus in agent mode only, so it's not acting as a data store, it will then use the Opni agent as a remote write endpoint, and then the Opni agent will be responsible for authenticating, tagging the metrics, and sending them through to the central Cortex store. We can now look at what it looks like to install that. Now to get logs and metrics, we can bootstrap a downstream cluster. Again, we've got a freshly set up cluster here. This one's an RKE cluster, and again, it's been set up with Cert Manager, which is a prerequisite for the agent as well. So the first thing we have to do is go into the management UI that we saw in the central cluster demo and create a token that we can use to bootstrap the cluster. So we're going to click create, and then we can choose an expiration. We'll choose 1 day for this one and create that token. So this gives us the time to live and how many times it's been used to bootstrap a cluster, so we can keep track of that if we need to for security purposes. So we can then go to clusters and choose to add a cluster. And if we select a capability, it doesn't matter which one, and we select the token, we can then see that we've got some manual install information here. So going back to our downstream cluster, again we're going to set up a repository. So this is just like what we did for the central cluster. Use charts repo. And then we will need to choose to install the Opni agent. So again, we'll remove the other charts and we'll choose to select the Opni agent. So we'll just put it in the Opni system namespace. We'll call it Opni agent. So now we can see that we have these 3 questions. So we're just going to put the Opni gateway and Rancher side by side so we can take a look at both of them. And we can see that these roughly line up here with the manual information that we require. So we can copy the token ID, put that over there, copy the cert pin. So this is security to make sure that there is no man-in-the-middle attack. And then we need a gateway URL. So this is what we put in when we installed the Opni central cluster, and it's what we've set up and how we've exposed our Opni gateway API. So that was gateway. And then by default, the API is on port 8080. So we put that in the end. Then we can choose which capabilities we're installing into this cluster. So we'll choose metrics, and we'll install the Prometheus operator as well. So we've got something to gather those metrics. And we'll install the logging agent. Because we've got a trusted certificate for OpenSearch, we don't need to disable the OpenSearch TLS verification. And we'll select the distribution of the downstream cluster we're bootstrapping, which in this case is RKE. And then select install. So now that it's successfully installed, we can see here that we have a bunch of pods that have been set up. And if we go back to our clusters, we can see here that we now have a cluster listed, and it's showing both the logs and metrics capabilities. So if we go back to our OpenSearch dashboard, we should be able to see logs starting to come through. And so here under Discover, we can see that indeed there are logs beginning to come through. These are just standard Kubernetes control plane logs. And as we sit for some more time, we can see here that logs are continuing to flow from our downstream cluster. If we go back, we can see that we're also getting a number of metrics come through. So we've now successfully bootstrapped a downstream cluster into our Opni central cluster. And with that, I will hand over to Yingbei for the Opni AI part of the session.
Hey everyone, this is Yingbei. Next, I'm going to talk more technical details about Opni AI Ops. Opni AI Ops is Rancher's open source project that applies AI technologies to IT operations. The goal is to help operators to reduce the mean time to detection and resolution of issues in the Kubernetes clusters. This tool will produce AI insights for observability data include logs, metrics, and traces. Anomaly detection on logs is where we started this project with. In the world without AI ops, logs are typically consumed reactively. That's to say, operators won't dive into logs until there is an outage or incident occurs. Also, searching for the root cause in a sea of logs is painful because it's really clueless to find out where to start searching. For example, grep for keywords such as error or failure is usually insufficient, and the log level of logs isn't something people can really rely on either. This is what makes log anomaly detection the hardest of the three types of observability data, and it is exactly why we step in here. Opni AIOps proactively monitors Kubernetes logs and captures those anomalous pattern logs in real time, which will significantly reduce the amount of time to detect and resolve the incident. We will see how it works in a demo soon. So far, Opni AIOps support AI insights on control plane and etcd and Ranger logs, but we will reintroduce the support for anomaly detection on workload logs later this year. For metrics, Opni AIOps features metric anomaly detection on Kubernetes golden signals, and the modeling on user-selected SLO metrics will be supported in our next release. For traces, we will introduce service-level anomaly detection. So, how does Opni AIOps differentiate it from other AIOps tools in the market? First of all, our product has its own infrastructure, Opni Logging and Opni Monitoring, as the observability tool and long-time data storage. So you really have everything in one bundle, while most of the other AIOps tools are just connectors so that users will have to expose their data to external tools. Second, Opni AIOps doesn't require any AI knowledge from user to configure or set up the AI models. That makes it really easy to get started with. What's more, as Opni sits in the Rancher ecosystem, SREs and operators can take immediate actions to patch their clusters as soon as some issue is detected. Lastly, Opni AIOps is the only open source AIOps tools in the market. So I think the easiest way to understand how helpful our AI insights are is by looking at a demo. Amartya is going to walk you through the story of how he used Opni AIOps to crack a real-world incident.
All right, so here we are going to see a demo of Opni log anomaly detection. Throughout this demo, I will be playing the role of an SRE. An SRE is typically in charge of the uptime and performance of a cluster. Let's say, for the purpose of the demo, I am responsible for this RKE1 cluster with 3 control plane and etcd nodes and 1 worker node. Let's head to the Opni dashboard where users can consume the AI insights generated by Opni. As seen from the dashboard, everything is in a pretty stable state. And as the operator of the cluster, I know everything is good. Now, what I'm going to do is inject a failure into our Kubernetes cluster and subsequently try and deploy a workload. The failure should prevent us from deploying this workload. Now, I'm going to try and deploy this workload demo-opni. All right, I'm coming across this error here, so let me investigate in the Opni UI. We see a lot of anomalous log messages right now, especially in the Kube API server. So let's take a look there first. Okay, So I'm looking at the kube API server logs right now. And I'm seeing that the API server received an error. And if we keep going down, let's look at this message over here. So it's saying that it failed to connect to this IP address over here, the internal IP address of a node at port 2379. And port 2379 is actually the port exposed by etcd for client connections. So etcd will expose two ports, 2379, which as we saw is for client connections. So components like the kube API server will use that to attempt to connect. And the other port exposed is 2380, which is used for peer communication with other etcd nodes in the cluster. So let's go back and observe the etcd logs that were marked as an anomaly. Okay, so it appears for the log messages for the etcd component, it appears that there's we're seeing a rejected connection from this IP address. But let's look a little further to see if we can find anything else that might be able to give us a little bit more information. And so a lot of these messages are the same. Okay, look over here. This message is talking about how an etcd node is unsuccessfully attempting to conduct a health check on its peer etcd node. And we can see over here that it's trying to dial this address at port 2380, but it is unsuccessful. So now what we would want to do to further understand what's going on, we should SSH into the node that's appearing in the log message. This IP address is the internal IP address, so 172.31.12.174 of the node, so that we can use that to find which node is being referred to, and then we can SSH into that node. So let's go back into the Rancher UI. Within the Rancher UI, we are seeing that this node, 172.31.12.174, is pointing to this node, demo-etcd-cp-nodes1. And here's the external IP address. So we can now SSH into this node to investigate further. At this point, there are many possible causes for this issue. So let's take a step back to understand what happens when the kubectl command is used to deploy a workload. In a normal system, the kube scheduler will maintain a queue for pods that need to be scheduled onto a node, and it will be listening to the kube API server. When a pod is to be created, the metadata of that pod is written into etcd by the kube API server, and the scheduler is going to be listening to the pod status. When a new pod is added, the pod is then added to the queue. The main process of the scheduler will extract these pods from that queue and assign nodes for these pods to run on. So what is happening in the situation is that the kube API server added a pod to this pod queue. However, when the kube API server tries adding this new configuration to the etcd, it is unable to connect to the etcd. So that data is never placed into etcd, and thus that's why we are seeing that error over here. So now that we have more context about the expected flow of events, I have SSH'd into the node, and I am going to investigate the etcd container running, since the logs indicate that there is some problem with etcd and network connectivity. So when I tried to deploy my workload in a normal setting, the metadata from the deployment that is to be created should be written into etcd by the kube API server. Since we are seeing that the etcd seems to be having trouble with connectivity, we should investigate the deployment metadata contained within this etcd instance. We can achieve this through the use of etcd-ctl, a command line tool for interacting with the etcd server. So let us first check the keys present within etcd using etcd-ctl. So we will be running this command over here. We will be using etcd-ctl. So since I was running my deployment within the Opni system namespace, this is what we want to really look for. Thus, we can see here that the etcd does not have any data about the demo-opni workload I was trying to deploy here. So the kube API server was unsuccessful in writing the metadata to etcd. So now we can understand that there was some specific issue with etcd that caused this problem. And in this case, the fault I injected caused network corruption of the etcd container. So that was why I was unable to deploy the workload. Now, let's go back to OpenSearch Discover. In the last hour, we see that there were over 100,000 logs processed. Now, let's go to the Opni UI. By comparison, we see that there are less than 2,000 logs that Opni specifically marked as an anomaly, and thus it narrows down the scope drastically of the number of logs I need to search. Additionally, by breaking down the anomalies by the control plane component, that makes everything much more organized and easier to process. So in this demo, we showed Opni log anomaly detection. To see a demo of metric anomaly detection, check out our website, opni.io, for another video where we will go over that use case.
Next, let's dig a bit more deeper into each component of Opni AI Ops. Let's start with log anomaly detection. Our log anomaly detection will classify logs into two categories, either normal, which basically means the log messages are all good, or anomaly. Those are the logs operators should immediately pay attention to. We have one portrayed model that focuses on control plane and etcd logs, and another model for rancher logs. They are all maintained by SUSE rancher. At this moment, our models support RKE1, RKE2, and K3s clusters with any Kubernetes version greater than 1.21. We will continuously enhance our models to support more Kubernetes distros and versions in the future. Our log anomaly detection model is an ensemble of two submodels, the log templatization model and an advanced deep learning model. I will walk through them one by one. The log templatization model extracts and generates static string templates from logs. These logs can then be used by matching to any incoming logs. Compared to simply gripping for keywords, the error keywords, such as error or failure, this model is essentially gripping for known anomalous log templates. So it's really like a smarter way of doing keyword scrapping. On the other hand, our pre-trained deep learning model is an advanced model built on top of the transformer, which is probably the most popular model in natural language processing research field these years. You might ask, there are many log anomaly detection algorithms. Why did us choose this model? Let me explain it. Algorithms of log anomaly detection can be categorized into supervised learning and unsupervised learning. The supervised learning models typically requires many human annotated log data, which is time-consuming and very expensive to collect in real world. As for the unsupervised models, the transformer model is the only model that can capture complicated anomalous pattern logs by learning semantic meaning from log messages and without any strict assumptions. While some other algorithms, for instance, the PCA model extract hidden patterns of logs by transform log message into matrix and then do dimension reduction. However, it can't learn complex patterns from large scale of logs, and it's not robust. Another deep learning algorithm called DeepLog is a convolutional neural network model, and it's modeling on sequence of logs, but it makes such a strong assumption that all logs should be streaming in order by its timestamp, which is very difficult and unrealistic to satisfy in a production environment. For our deep learning model, we also did many optimizations, includes parameter tuning and prediction caching in order to improve it so that it doesn't require a GPU to serve. Now let's talk about metric anomaly detection. Metrics are useful because it provides a high-level picture of Kubernetes system. Operators can use metrics to monitor the health of their clusters at a glance. For instance, how is average memory consumption of the servers, or the number of unhealthy pods in the system? What people usually do is set up a static threshold value for each metrics and raise an alert if any of them is violated. However, nowadays, as the size of clusters and workloads scales up, it becomes more and more difficult for operators to correlate metrics and understand what is a normal state and what is the proper threshold of their clusters, especially when they have more and more machines to look after. This is something metric anomaly detection can help with. Rather than static threshold, metric anomaly detection can dynamically generate threshold values by identifying anomalous patterns that deviate from normal behaviors of time series metrics. In Opni AI Ops, we use a general method SARIMA as our base model, which is one of the most popular statistical learning model widely used by many other AI Ops tools too. SARIMA is short for autoregressive integrated moving average with seasonal pattern expansion, where autoregressive indicates the model is a regression model that forecasts future values from its past observations. Integrated represents the action of differencing of raw observations to make the time series data stationary. And moving average refers to incorporate past forecast errors into the regression model. With such a structure, this model is then good at learning the trends and seasonal patterns in time series metrics data. And what's more, it can be fit to various types of Kubernetes metrics with a good speed and accuracy balance. Currently, our product supports modeling on several Kubernetes golden signals. We're going to extend it to support user-created service-level objective metrics later this year. Next, I'd like to do a quick feature comparison between AI Ops tools of Opni and Datadog and OpenSearch. Compared to Datadog AI Ops, which is a SaaS tool, Opni AI Ops is open sourced and it has more advanced log anomaly detection models to detect complex anomalous logs. Compared to OpenSearch, they do provide free anomaly detection tools too, but users without enough AI knowledge would not be able to set up and configure their AI-based monitors, while Opni AI Ops will provide stronger models without any AI model configuration needed. Before we end this session, I'd like to share a few useful links you can check out. That's everything for today. Thank you for watching.